By 1999, humans could have been walking on Mars. Not in some distant fantasy future, actually there, boots on the ground, conducting science on another planet. The plan existed, the technology was ready, the cost was affordable, but instead, we chose to build a space station that goes nowhere, orbiting just 250 miles above Earth's surface, closer to you right now than Los Angeles is to San Francisco. This is the story of Mars Direct. The mission architecture so elegant, so cost-effective, that it terrified the very institution designed to explore space. And it's the story of one decision in the early 1990s that cost us 30 years, and counting. Picture a conference room in 1989. Robert Zubrin, a young aerospace engineer at Martin Marietta, sits listening to NASA's latest presentation on how to reach Mars. He's frustrated, scribbling calculations in his notebook, watching his dream of the red planet slip away behind impossible price tags and bureaucratic complexity. This is the moment when America's best chance to reach Mars begins to die, not from lack of vision, but from an abundance of it gone terribly wrong. Just months earlier, on July 20th, 1989, the 20th anniversary of the Apollo 11 moon landing, President George H.W. Bush stood on the steps of the National Air and Space Museum and announced the Space Exploration Initiative. It was bold. It was inspiring. It called for a human mission to Mars, the first presidential Mars mandate since Kennedy's moonshot speech. The nation's space engineers felt that old Apollo electricity in the air again. Finally, after decades of shuttling in circles and dreaming small, America would think big once more. NASA responded with what became known as the 90-Day Report, a sprawling multi-decade plan requiring lunar bases, orbital fuel depots, massive infrastructure assembled in space, and a complexity that would make the Apollo program look like a high school science project. The document was thick, the timeline was long, the architecture was impressive, and then came the number that killed it all, approximately $500 billion. In 1989 dollars. To put that in perspective, the entire Apollo program, the one that actually put 12 men on the moon and brought them home, cost about $25 billion in its time, which adjusts to roughly $150 to $160 billion in today's money. NASA was proposing a Mars program that would cost more than 3 times Apollo's inflation-adjusted price tag. Congress didn't just reject it, they laughed it out of the room. The Mars dream appeared over before it truly began, strangled by its own ambition and buried under an avalanche of zeros. But in that conference room, Zubrin wasn't just frustrated, he was calculating. He saw the fundamental flaw in NASA's thinking. They were trying to build a highway to Mars when what was needed was a covered wagon, simple, direct, self-sufficient. Every element of NASA's plan assumed you had to bring everything from Earth. All your fuel, all your supplies, all your redundancy. It was like planning to cross the Atlantic by first building a bridge. And then Zubrin had an epiphany, the kind that changes everything. What if you didn't bring all your fuel from Earth? What if Mars itself could provide the fuel for the return journey? This single insight would transform an impossible mission into an affordable one. Zubrin teamed up with David Baker, a fellow engineer at Martin Marietta, and together they worked nights and weekends developing what they called Mars Direct. There was excitement in their collaboration, the thrill of solving an impossible problem with elegant engineering. They weren't inventing new physics or dreaming up technologies that didn't exist. They were simply asking the right question: how do you get to Mars with what we already have? The core innovation was something called in situ resource utilization, ISRU for short. The concept is beautifully simple. Mars's atmosphere is 95% carbon dioxide. Bring a small amount of hydrogen from Earth, run it through a device called a Sabatier reactor with Martian CO2, and you get methane fuel and water. The chemistry is straightforward. Carbon dioxide plus hydrogen yields methane and water. It's not science fiction, it's not even particularly advanced chemistry. It's a reaction discovered in 1897, and it works with an efficiency of approximately 90% in laboratory tests. This single innovation, making fuel on Mars instead of hauling it from Earth, reduces launch mass by 80%. And when you reduce launch mass by 80%, you reduce cost proportionally. Suddenly, that $500 billion nightmare becomes a $50 billion reality. A $350 billion savings from one clever idea. The architecture Zubrin and Baker designed was elegantly simple. First, you send an Earth return vehicle, unmanned, to Mars. It lands, extends its equipment, and begins sucking in the thin Martian atmosphere, processing it through the Sabatier reactor, manufacturing methane fuel and oxygen for the return trip. This takes about 10 months. Only when the ERV signals tank full do you send the crew in their habitat, knowing with certainty that their ride home is fueled and waiting. No lunar bases needed, no orbital assembly, no fuel depots floating in space. Just 2 heavy lift launches per mission. One for the return vehicle, one for the crew habitat. Mars Direct was to traditional NASA planning what Apollo was to a space shuttle program. Direct, simple, with minimal infrastructure, whereas NASA's plans required complex support and maintenance systems sprawling across cislunar space. In 1990, Zubrin and Baker presented Mars Direct at the Case for Mars conference in Boulder, Colorado. The reaction from working engineers was electric. They immediately grasped the elegance. Here was a plan that didn't require inventing new physics or developing technologies decades away. It used proven rockets, proven chemistry, and proven life support systems. The math worked, the physics worked, the engineering worked. But NASA management's response was more cautious, more political. There were nods, certainly. There were expressions of interest. But there was also something else: hesitation. The kind of institutional hesitation that comes when someone shows you a solution so simple it threatens to make your complex organization look foolish for not thinking of it first. Over the following months and years, Zubrin found himself in an increasingly frustrating position. NASA's Johnson Space Center invited him to present. The technical staff was enthusiastic, running their own analyses that confirmed Mars Direct's feasibility. Every time Zubrin presented the numbers, the engineers in the room started nodding. They understood immediately. This could work. This could actually work. But it was the management who hesitated. Mars Direct was too radical, they said. Too risky. Too much of a departure from proven approaches. Never mind that the proven approaches had produced a price tag that guaranteed Mars would remain unreachable. Never mind that Mars Direct used more proven technology than NASA's orbital assembly plans. The word radical became a shield against change. NASA did incorporate some Mars Direct elements into a modified plan they called the Design Reference Mission. But in the process of institutional revision, they added back complexity, orbital assembly, and inflated costs. It was like watching someone take a sleek sports car design and transform it back into a bus because buses are what we know how to build. Then came the breakthrough that should have changed everything. Zubrin and Baker's team successfully demonstrated a Sabatier reactor in the laboratory, proving ISRU worked. They watched methane flow from Martian simulated carbon dioxide, saw the efficiency numbers hit 90%, and believed, truly believed, that this proof of concept would convince NASA leadership. How could you argue with working hardware? How could you call something too risky when it was literally producing fuel in front of your eyes? But institutional inertia is a powerful force. Mars Direct threatened existing programs, centers, and contractor relationships. It was too disruptive. It would require NASA to reorganize, to shift resources, to admit that simpler was better. And behind the scenes, a different priority was emerging in Washington, one that would doom Mars Direct before it ever got a real chance. While Zubrin fought to keep Mars Direct alive, NASA's leadership faced a choice that would define space exploration for the next 3 decades. In the early 1990s, with budgets tightening and political winds shifting, NASA had to choose between competing visions, Mars or the space station. The International Space Station offered something Mars didn't: continuous work for multiple NASA centers, contracts for established aerospace companies, and diplomatic benefits with Russia and international partners. It was politically safe. It wouldn't require any bold new technologies or risky missions. Astronauts wouldn't die on another planet. They'd float safely in low Earth orbit, close enough for emergency evacuation if needed. From a political perspective, the choice was easy. The space station meant jobs in Houston, Huntsville, and Florida. It meant international cooperation at a time when the Cold War was ending and America needed to engage Russia constructively. It meant steady, predictable work rather than a high-risk, high-reward mission to another planet. The space station became the politically driven decision that killed America's best chance at an early human Mars landing. Not because anyone explicitly voted against Mars, but because in the zero-sum game of NASA budgets, choosing the station meant not choosing Mars. Here's the tragic irony that should haunt every space policy decision. The International Space Station would eventually cost over $100 billion, more than twice the cost of Mars Direct, and accomplish far less in terms of exploration. For the price of a laboratory orbiting 250 miles above Earth's surface, closer to you right now than many people's morning commute, we could have sent humans to another planet 140 million miles away. By the mid-1990s, NASA's budget was locked into space station construction. Mars Direct was effectively dead, though never officially canceled. It simply faded from official planning documents, replaced by vague promises that the station would serve as a stepping stone to Mars. But a stepping stone implies you eventually take the next step. The station didn't step toward Mars. It anchored us in Earth orbit for decades. The decision wasn't made on technical merit. It was made on politics, jobs, and institutional preservation. Mars Direct was too efficient, too simple, too disruptive to the established order. It threatened to prove that NASA didn't need sprawling infrastructure programs to reach Mars. It threatened to show that bold exploration could be affordable. And that was more dangerous to the institution than any Martian dust storm. Zubrin, now decades older, has watched the technologies he proposed in 1990 finally being tested and validated, but 30 years too late. The three core technologies of Mars Direct, ESAU, direct-to-Mars trajectories, and compact nuclear reactors for surface power, have all proven viable, every single one. In April 2021, NASA began testing MOXIE, the Mars Oxygen ISRU experiment, on the Perseverance rover. It's a small device that does exactly what Zubrin proposed in 1990. It sucks in Martian atmosphere and produces oxygen through chemical processing. And it works. It works beautifully. The concept Zubrin championed 3 decades ago is now proven hardware operating on Mars. SpaceX's Starship is designed around the same direct-to-Mars philosophy Zubrin advocated. No orbital assembly, minimal infrastructure, direct launch from Earth to Mars surface. Elon Musk has openly acknowledged Mars Direct's influence on SpaceX's mission architecture. The private sector is building what NASA refused to. NASA is developing kilopower reactors for Mars surface missions, compact nuclear technology that provides reliable power in the Martian environment. The Kilopower project has demonstrated a 1 kilowatt prototype on Earth, proving the concept works. These are the same compact nuclear systems Mars Direct required for surface operations. The bitter truth, every key technology of Mars Direct has been validated. We could have done this in the 1990s. The engineering was sound, the chemistry was proven, the mission architecture was viable. We didn't lack the capability. We lacked the will. There's a human cost to this delay that's harder to quantify, but no less real. An entire generation of engineers and scientists who dreamed of Mars have retired or died without seeing humans reach the red planet. The children who watched Apollo and were inspired to become aerospace engineers are now in their 60s and 70s. They spent their careers building space stations that go nowhere instead of spacecraft that go everywhere. How many years did we lose? What discoveries weren't made? What inspiration was squandered? If Mars Direct had been approved in 1991, the first crew would have landed on Mars in 1999. Think about that date. 1999, the year The Matrix was released, the year people worried about Y2K, the year we could have been walking on Mars. The timeline is straightforward. If the program had started in 1991, the first Earth return vehicle could have launched in 1997, spending 10 months in transit and 10 months making fuel. The Crew Habitat launches in 1999, lands in 2000. By now, in 2024, we could have conducted 3 or 4 Mars missions, assuming one mission every 26 months, the interval when Earth and Mars align favorably for travel. Imagine that alternate timeline, By 2024, we could have permanent habitats on Mars, extensive geological surveys, and definitive answers about whether life ever existed on the red planet. We could have tested closed-loop life support systems, advanced ISRU technology, and compact nuclear power in actual Martian conditions. All of these technologies would now be mature, proven, and applicable to future deep space missions. The inspiration factor alone is staggering. An entire generation grew up with Apollo, watching humans walk on the moon, and it produced a surge of scientists, engineers, and explorers. Imagine a generation growing up with regular Mars landings, with humans living and working on another planet as a normal part of their reality. The scientists and engineers that would have produced, the problems they would have solved, the dreams they would have dared to dream. The geopolitical reality would be different too. America would have an unassailable lead in space exploration, rather than watching China plan their own Mars missions and wondering if we'll be beaten to the red planet the way we were nearly beaten to the moon. But here's the twist in this tragedy. Mars Direct isn't dead. Its DNA lives on in current plans. SpaceX is building Starship. NASA is testing Moxie. The kilopower reactors are in advanced prototype and demonstration phase. The technologies are finally being developed, just 3 decades late. There's still time, barely, to reclaim some of what was lost. The question haunting the space community is whether we've learned the lesson. Are we about to make the same mistake again? As NASA plans the Artemis program to return to the moon, are we building another sprawling infrastructure program that consumes resources without advancing the ultimate goal? Are we choosing the safe, politically palatable path over the bold, transformative one? We began with a simple question. Why aren't we on Mars yet? The answer isn't that we lack the technology, the knowledge, or even the money. We're not on Mars because in the early 1990s, when we had a clear, affordable path to get there, we chose institutional comfort over bold exploration. Mars Direct revealed an uncomfortable truth about NASA and space exploration. Sometimes the biggest obstacle to reaching the stars isn't the vast distance or the hostile environment. It's the bureaucracy and political calculations that keep us grounded. The cost of playing it safe isn't measured just in dollars or years, but in lost inspiration, missed discoveries, and an entire generation that could have grown up as a spacefaring civilization, but didn't. The technology Zubrin proposed in 1990 is finally being validated today, 30 years late. Every major element of Mars Direct has been proven viable. The only thing that wasn't viable was the political will to pursue it. Somewhere in an alternate universe, there's a version of humanity that took the bold path in 1991. They've been living and working on Mars for a quarter century now. They've answered the question of whether life ever existed on another world. They've inspired millions of young people to become scientists and engineers. They've proven that humans are not bound to a single planet. We can't get back those lost decades, but we can choose, right now, not to waste the decades ahead. We can choose to learn from the mistake of Mars Direct. We can choose bold exploration over safe incrementalism. We can choose to ask not what's politically comfortable, but what's humanly possible. The plan existed, the technology was ready, the cost was affordable. We chose not to go. That choice cost us 30 years. The question is, what will we choose next? If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.